You know, sometimes you're given a polynomial and you're told to find out how many possible roots the polynomial may have, and that is where Descartes' rules of signs comes in. So come along with me. As we study through the Descartes' rules of signs, we're going to understand the purpose of this rule. Why do we even need it? We're going to look at the steps for identifying the number of positive roots, the number of negative roots, and I'm going to introduce you to a very interesting concept called the PNI Table, and we're going to also use all of these information to we're going to use the information to create our own PNI tables for the polynomials that are given. So why do we need the Descartes rules of signs? It helps us identify the type, very important, and number of zeros of a polynomial. Zeros are also known as the roots. They're also known as the x-intercepts of a polynomial when a graphing calculator or a graph are not available. Of course, if you have a graph, it's easy to, if you have a graph or a graphing calculator, it's easy to tell all of these things, but Descartes allows us to look at the possible number of roots that are positive, negative, and also imaginary. Imaginary will not actually be on the graph because imaginary means that it cannot fit on the number line, and you know our graph is mostly about number lines. And so we're going to use this rule to identify the possible number of positive, negative, and imaginary roots of polynomial functions. Let's start with the number of positive roots. To do this, we're going to first write out the function completely, and then we're going to pay attention to the signs of the coefficients of each of these terms. And the reason why this is important is we have to take note of where the signs are changing from one coefficient to the other. So we're looking at subsequent coefficients, one after the other. And this number we get is going to represent the maximum number of positive roots of the polynomial. And every other possible number of positive roots is going to be a factor of 2 less. It cannot be greater. It has to be a factor of 2 less than the maximum. And you cannot get a non-negative, you cannot get a negative number. They all have to be positive. You can get 0, but you cannot get a negative 1 and lower. So let's try to use this to answer a sample question. So find the possible number or numbers of positive roots of the function. So the first thing we do is we write the function. The function is already properly written. I'm going to put a positive here just so that we understand that this is positive. Okay, so this function is 6x to the 5th power plus 7x to the 4th power minus x cubed plus 11x squared minus 8x minus 15. We don't actually care what the value of the coefficient is. We only care about the sign. So what we're going to do here is look at where the sign changes. I'm going to take note of that. From positive to positive, there's no sign change, so I'm going to ignore that. From positive to negative, I have one sign change. I'm going to represent it this way. From negative to positive, I have another sign change, so I'm going to create a loop right there. And then from positive to negative, there is another sign change, create another loop. Negative to negative, I have no sign change. No sign change, so I have to ignore that. So we have 3 sign changes. So this is 1, 2, 3. So what we're going to see here is the maximum number of positive roots of this function is going to be 3. Other options or other possible number of positive roots will be 3 minus 2, which is equal to 1. So the possible number of positive roots are going to be 3 and 1. So those are the possible number of positive roots of this function. And when we get the PNI table, we can see different combinations of this to actually come up with, I mean, you will not know for sure until you actually go through the exercise of using all the theorems and the remainder theorem and all the rules that you may have to actually identify these roots. But this just gives you a sense of what you should be working toward. Now let's talk about negative roots. Slightly different. There's an additional step here. We're going to write out the function completely. Then we're going to replace every instance of x with negative x, which we can also look at that as evaluating f of negative x. And then what we did for positive after that is going to be the same. We're going to take note and count instances where the signs are changing, and that would always represent the maximum number of negative roots. And of course, like I said earlier with the positive roots, the other possible choices or possible number of negative roots would be a factor of 2 less than the maximum that you arrived at. So let's go ahead and try to do this one here. So we're looking at this function here, 5x to the 5th power minus 7x to the 4th power minus 6x to the 3rd power plus 11x squared plus 3x plus 9. And we want to find out the possible number of negative roots. So our first step here is going to be to find f of negative x. F of negative x. So for every instance of x, we're going to replace with negative x. So this is going to be 5. Then we have negative x to the 5th power minus 7 negative x to the 4th power minus 6 negative x to the 3rd power plus 11 negative x to the 2nd power plus 3 multiplied by negative x plus 9. Okay, so what's going to happen here is negative x to the 5th power, anytime you have a negative value and you're raising it up to an odd exponent, your answer is always going to be negative. So we're going to have negative 5x to the 5th power, and then negative x to the 4th power. Whenever every exponent, whenever you raise a number or a term to an even exponent, what you're going to get is always a positive number. So it's going to be minus 7x to the 4th power. This is minus 6 here. This is going to be negative. This is plus 6x to the 3rd power. This is going to be plus 11x squared minus 3x plus 9. So now what we're going to do here is we're going to pay attention to where the signs are changing. So our signs are changing right here. This is one change here. This is another change here. And then this is another change here. So we can say that the maximum number of negative roots is 3. Others would be 3 minus 2, which is equal to 1. So we have 3 and 1 as possible negative roots of the function. Now let's talk about the PNI table. The PNI table provides information on all the possible number of positive, negative, and imaginary roots of a polynomial, and the sum of these roots must be the same as the degree of the polynomial. We'll talk about that in an example soon. And the columns of the PNI table are positive, negative, imaginary, and total number of roots. So the sum of the positive, negative, and imaginary roots must be the same as the degree of the polynomial. So for example, if I have a polynomial that starts with x to the power of 6, it simply means that the degree is 6, so all my roots must add up to 6. So let's take a look at creating this table. So we said we have positive, negative, imaginary, and total. Create a PNI table for a polynomial with a degree of 5. So I'm just going to say I need to have 5 here. Has a maximum of 3 positive roots. So we start with our maximum, 3 positive roots, and a maximum of 1 negative root. So because of that, we need to find out how many imaginary roots we're going to have. So we have I, which is our imaginary root. 3 plus 1 is 4, is going to be 1, because all of this must add up to 5. So the other thing we can do here is we're going to subtract 2 from the positive to get 1. And the negative, we cannot change the negative because it's 1 here. 1 minus 2, remember we cannot have a negative value here. So this is going to be 1. And then we're still going to have 5 as the total number of roots. And this is going to give us 3. So this is a possible PNI table for this polynomial. So let's look at the steps in creating the PNI table. Like we did earlier, you want to find the maximum. We're going to use the Descartes rule to find the maximum number of positive and negative roots of the polynomial. We're going to put these numbers in the PNI table, and we're going to add as many rows as possible. And you're going to see, like you saw in the previous PNI table, we had 2 rows because we had 3 positive, 1 negative, and the only other option we had with the positive was go down to 1. It's possible if we have an even number of positive roots, we could go all the way to 0. But then an important thing to note here is that you have to remember that all your positive, negative, and imaginary roots must add up to, the count of them must add up to the degree of the polynomial. So let's go ahead and do some examples together. We're going to use the Descartes rule to identify the number of positive, negative, and imaginary roots of this function. So remember here, we're going to pay attention to sign changes. So I put a plus here. So let's go ahead. We have a sign change here. We have another one here. We have another one here. Another one here. Another one here. And then another one here. Let's find out how many loops we have. So maximum here is going to be 1, 2, 3, 4, 5, 6. So 6 is our maximum. Then we'll go ahead and find f of negative x, which is going to be 4 negative x to the 6th power minus 3 negative x to the 5th power plus 13 negative x to the 4th power minus 11 negative x to the 3rd power plus 9 negative x to the 2nd power minus 6 multiplied by negative x plus 7. So let's go ahead and simplify. So this is going to be 4x to the 6th power. This is negative, and this is going to be negative, plus 3x to the 5th power. This is going to be a positive here. This is plus 13x to the 4th power. This is negative, negative. We have plus 11x to the 3rd power. Then this is plus 9x squared plus 6x plus 7. So this is a unique situation because we actually had no sign changes throughout these. For f of negative x, we have no sign changes. So your maximum here is going to be 0. And so now let's go ahead and create a PNI table. So we got P here, positive, negative, imaginary, and then total. So our maximum here is 6. Don't forget that we have a degree of 6. So our maximum here, we can have 6 positive, 0 negative. This has to be 6. So this is going to give us 0. Then we go a degree of 2 lower, we get 4. We cannot have any negative, so it's going to be 0. We can have 2 here. It's going to give us 6. We have 2. We have 0. We have 4. And then we have 6 here. We have 0, 0, 6, and then we have 6. So this is what the PNI table for this polynomial is going to look like. And then let's go for one more example. Use the Descartes rule to identify the possible number of positive, negative, and imaginary roots of the function. So here we have positive right here, positive to negative, so we have 1. So your max here is going to be 1. And then for your f of negative x is going to be negative x to the 4th power minus 81. So it's going to be x to the 4th power minus 81. So your max here is also going to be 1 because we only have one sign change. So this is positive to negative. You have one sign change. Now what we're going to do here, the next step we're going to take here is to create our PNI table. PNI, and then we have total. Positive we have 1, negative we have 1, and we need to get to a degree of 4, so it's going to be 2. And you add this up, you must get 4. So this is what our PNI table is going to look like. The reason for this is because your positive has to be, the possible number of positive roots have to be reduced by a factor of 2. This is 1, and if we subtract 2 from 1, we're going to get negative. We are not allowed to have a negative number of positive, negative, or imaginary roots. So this is what our PNI table is going to look like.